Hello, multivariable calculus students. This is the second video for section 11.3, which is on partial derivatives. And we're going to talk now about functions with more than two variables. So for example, if we had a function f that was made up of input values x, y, and z, the partial derivative with respect to x would be defined in the limit definition as the limit as h goes to 0 of f of x plus h y and z minus f of xy z divided by h. So you can see that the formula is very similar to what we had on the previous page for partial derivatives. This time we just have that third element z as an input value. So this would be the partial of f with respect to x, and you could see the similarities if we did the partial with respect to y or with respect to z. All right, we're going to go ahead and try one of these in example 5. So we're going to find the first partial derivatives given this function of 4 variables. So we have f of x, y, and z. So the partial derivative with respect to x means that we let both y and z be constants. So we have the derivative y e to the xy times the natural log of z. So keep in mind that when we take the derivative of e to the xy, we get e to the xy and then times the chain rule. So the derivative of the exponent is going to be y because it's with respect to x. So remember, when you're taking, for example, let's go back just for a minute to single variable calculus. If you were taking the derivative of e to the 2x, you would get e to the 2x times the derivative of 2x, which is 2. That's just what I'm doing here, but instead of the 2, I have a y, basically, and the y is a constant. The natural log of z is also a constant, and that just sort of tags along with the derivative. Okay, if we have the partial derivative with respect to y, it would be a very similar situation where we would have the derivative of e to the xy, but we're going to multiply by x this time because of the chain rule, and then we'll, of course, have the natural log of z. And then the last one, we have the derivative with respect to z. So e to the xy is a constant, and the derivative of natural log of z is 1 over z. So we could write that as e to the xy divided by z if we wanted. And those are your first order partial derivatives for f of x, y, and z. All right, the higher order derivatives, the notation often will look like this, where we have f of xx, or we have f of xy, or f of yx, or f of yy. You may have the differential form. So for example, this could be the the partial derivative with respect to x of the partial derivative of f with respect to x. So you're taking the second derivative, which could look like this. And then I'll pause and fill out the other ones so you can see the other forms as well. Okay, so here are the other forms for those higher order derivatives. And again, you can see the similarities to single variable calculus. Of course, some of this where we're taking the derivative of possibly x first and then y, that certainly looks a lot different than what we've seen in the past. Here's a quick example for you for number 6, and we're going to do the second partial derivatives of this particular function. We're going to start with the first order partial derivatives. So we're looking at the partial with respect to x, which is 3x squared plus 2xy cubed. And we have the partial with respect to y, which is 3x squared y squared minus 4y. And we'll go ahead and start with the partial of f with respect to x and then x again. And so again, what we're going to do is we're just going to take the first partial with respect to x and do the derivative again now with respect to x a second time. And we get 6x plus 2y cubed. We can then take a look at the partial derivative first with respect to x and then with respect to y. So again, we're going to follow the first partial with respect to x and then do the derivative with respect to y. So again, when we're looking at 3x squared, the derivative of that is 0. And we have then 6xy squared. The partial derivative with respect to y first and then x gives us, again, we're going to go over here to the partial derivative of y first, and then we're going to take this derivative with respect to x. We end up getting 6xy squared, and then the partial with respect to y first, and then y a second time would give us 6x squared y and minus 4. You may notice that the middle partial derivatives, so we're looking at the partial derivative with respect to x and then y, and the partial derivative with respect to y and then x are the same. And this occurs most often. It's called Clerose Theorem, and I'll show it to you on the next page. All right, so here's the theorem, and basically what this says is that if the second degree higher order partial derivatives are existent on a small disk around a particular point, so in other words, around the point you're analyzing, if the second derivatives exist, then the partial second derivatives f of xy and the partial derivative f of yx is going to be identical. So in pretty much any case that we're dealing with in our particular course, this will be true. There are some rare cases where this is not true, and that is because the second order partial derivatives would not exist around the point you're trying to analyze. Okay, we're going to try example 7 given this information. So we have the first derivative with respect to x, which is going to be e to the x, and then sine of y, and then the first derivative with respect to y, which is e to the x, and then cosine of y. All right, the derivative f of x would be e to the x and sine of y. The derivative of xy is equal to the derivative of yx, and we can just double check that this is the case if we were to think of both. So if we would look at the derivative of f of x with respect to y, we would get e to the x cosine of y. And if we were to look at the derivative of the first partial derivative with respect to y with respect to x, we would get the exact same thing. And so we can see that those two are equal in this case. And then the derivative with respect to y and then y again would be negative e to the x and then sine of y. All right, let's move on to example 8. So we're looking at calculating a higher order derivative. So we're looking at a fourth part partial derivative here. So we're going to start with f of x, and f of x, or the partial derivative with respect to x, is going to be cosine of 3x plus yz. And then because of the chain rule, we have to multiply by 3. And let's just rewrite that really quickly so the next derivative is a little easier. Okay, so then we're going to take the next partial derivative with respect to x again. And again, the chain rule is going to dictate that we're going to take the derivative here of cosine, which is negative sine, but then we're going to take the derivative of the inside again because of the chain rule and get a 3. So I'm just going to save a little bit of time, and we'll make this negative 9 sine of 3x plus yz. And again, that times 3 to get the 9, that was because of the chain rule. Then we have our next derivative, which will be with respect to y. And so we'll have negative 9 cosine of 3x plus yz. And of course, in the inside, this time the chain rule will be based on the derivative with respect to y. So that would be times z. And I'll just rewrite that again so it's a little easier for our last derivative. All right, our very last one is going to be the derivative with respect to z. And if you notice, we have a product rule now because we have negative 9z times cosine of 3x plus yz. So we'll take the derivative of negative 9z to get negative 9, and we'll keep the second function the same. And then we will keep negative 9z, but then we're going to take the derivative of cosine, so we'll get a positive 9z sine of 3x plus y times z, and then we would multiply that by y, again because of the chain rule. So for our final answer, if we just write this in a slightly different form here, we'll have negative 9 cosine of 3x plus yz plus 9yz times sine of 3x plus yz. Okay, let's go on to the next page. All right, for example 9, we're just going to show Clerose theorem by finding the first partial derivative with respect to x. That's going to be secant squared of xy multiplied by y because of the chain rule. So I'm just going to write that a little differently here. And then we'll also have the derivative with respect to y, which is going to be secant squared of xy times x. All right, we're just going to show that Clerose theorem is true for this particular problem. And we have sort of an ugly product rule with chain rule built into this one. So when we're taking the derivative of yx, we get the derivative of the derivative of x, which is 1, times secant squared of xy plus x, and then we're taking the derivative of secant squared xy, which is first the power rule, so 2 secant of xy, then the derivative of secant, which is secant xy times tangent xy, and then the derivative of the inside of that, and again, it's with respect to x, so we're going to get times y. And I'm going to go ahead and rewrite that, simplify it down just a little bit. Okay, we're going to try to show then that if we were to take the second partial derivative first with respect to x and then y, we're going to get the same thing. So again, I'm up here looking at the very first partial derivative with respect to x. I'm going to take that derivative with respect to y now. So we get obviously the same kind of setup here, secant squared of xy, and then we have plus y times, and we're doing the power rule. Again, we're seeing a lot of similarities here, which is due to Clerose theorem. And then we're going to multiply by x that time, and you can see as we simplify this that we do get the identical second derivative, and Clerose theorem holds true for this one as well. Okay, so Clerose theorem obviously helps us with this type of situation where if we were asked for that particular derivative, we wouldn't have to do it both ways. We could just do it the one way. We know it's going to be true, but it also helps us for the higher order derivatives. So for example, let's say that you were trying to calculate f of x, xy. That's actually the same thing as f of x, y, x, and the same thing as f, y, x, x. So it may help us. For example, let's look at 10. If I was to take the derivative of f of the first partial derivative in terms of x first of f of x, y, z, I would get, let's see, y squared z cubed plus the derivative of arc sine is going to be 1 divided by the square root of 1 minus the quantity x square root z squared times, because of the chain rule, square root z. So that would be my first partial derivative. Then I would have to take the derivative with respect to z. Now you can imagine that this is not too bad, but here we're going to be dealing with the quotient rule, chain rule, and it gets really ugly pretty quickly. If instead we were to take and change this using Clerose theorem, and we were to take the partial derivative first with respect to y, notice that this entire portion is a constant, and therefore the derivative is 0. And so we're left with simply 2xyz cubed. And it seems so much easier now, because then we could take, for example, the derivative with respect to x, and we would get 2yz cubed, and then we could finish it off and take the derivative with respect to z to get 6yz squared, and by Clerose theorem that is equal to what we were originally asking for. So you can see that changing the order actually can have a lot of benefit algebraically. Not always, but many times the derivative order is going to help us as we progress through a problem. Okay, let's take a look at our last page. Okay, on this last page, we're going to take a look at graphs. We're going to look at first the contour in example 11. So we're looking at the partial derivative with respect to x at the point 2, 1, and that point looks like it's about right here. And if we're looking at the partial derivative with respect to x, we're looking in the positive x direction, and we're asking ourselves the question, what are the values of f doing on the contour? In this case, they're increasing, so therefore the sign of this first derivative with respect to x is positive. If we look at the derivative with respect to y of 2, 1, we'll ask a similar question, except this time we're going in the direction of positive y, and these contours are decreasing, and so this is going to have a negative value because that slope is decreasing. All right, a much harder concept would be a surface and looking at the derivatives. So this set is in your notes, in your homework problems. This is problems 5 through 8 in the textbook. And we're going to look at 5a first. So we're looking at the point 1, 2, and our question is, as we travel in the positive x direction, is the slope increasing or decreasing? That's really just the slope of the tangent line at that particular point. So we're looking at really what is that slope there, and that is a positive slope. In other words, that surface is rising along the z-axis. If we take a look at the same exact point but in the direction of y, so again we're asking ourselves the question, is that slope at that point in the direction of positive y a negative slope or a positive slope? And in this case it's a negative slope because the surface is going down at that point. If we take a look over on the other side at the point negative 1, 2, the slope in the x direction, so again we're looking at the tangent line like this, that slope is going to be negative. In other words, at that point you're looking down along the surface. And if you look in the direction of positive y, the slope of that tangent line is also negative at that particular point. Okay, so those are the first derivatives. Those are a little bit easier, I think. Second derivatives are a little bit more difficult. So when we're looking at 7a, we're looking at the second derivative, both with respect to x. We're looking at the rate of change of the first derivative with respect to x in the direction of positive x. So here's what this means. If we're sitting at the point negative 1, 2, and we are looking in the direction of positive x, and we begin to sort of, walk in that direction and analyze the slope of the tangents as we travel in the positive x direction, the slopes of the tangents are increasing. In other words, the graph is getting less steep in the negative direction. It's actually starting to flatten out. If you think back to last year or the previous year, this is more of a concave up style curve. That's what we're talking about doing. This is going to have a positive second derivative because of that behavior, that concavity behavior. Now, if you're taking a look at the exact same point, but in terms of the second derivative in terms of y in both cases, it's really kind of the opposite. So you're looking in the positive y direction, but you're looking at how do the slopes change as you travel in the positive y direction, and you're getting steeper and steeper. In other words, again, if you revert this back to the idea of concavity, this curve is concave down, and that second derivative is therefore negative. Now, the second derivative with respect to two different variables, that becomes even more difficult. So let me try to communicate what A for number 8 and B for number 8 is asking. So that the second derivative there is asking for the rate of change of f of x, the first derivative with respect to x, in the y direction as you look at the positive x direction. Here's what this means. So you're sitting at this point, and let's say this is you, and you are traveling in the positive y direction. So you're walking along the curve at that moment, but you're not looking in that direction you're walking. You're looking at the positive x. So you're looking at what's happening to the surface as you are traveling along the positive y. So you're looking off to your side. And if you notice, the surface is getting steeper and steeper in the positive direction, which would cause this second derivative to be positive. So I'll say that again. So you're traveling in the positive y, but you're looking at the surface as you look at the positive x direction, and that surface is getting steeper and steeper in the positive direction, which means that second derivative is positive. If we skip over and look at the other point and do the same exact thing, so if this is you traveling in the positive y direction, but you're looking at what's happening to the slopes in the positive x direction, those particular slopes are actually getting steeper, but in the negative direction, which means that that second derivative is in fact negative. So as you travel along the positive y, you're looking at steeper and steeper downward slopes, which means the second derivative is negative. Okay, that does it for section 11.3. Thank you.